Hi, I'm Ben-Yaakov. This presentation is entitled Intuitive Explanation of a Flying Capacitor 3-Level Buck Converters. So why do we like to have multi-level converters? What are the benefits? What are the advantages? Well, as it turns out, we can get lower switching losses, we can get lower conduction losses, and also we can get a lower switch voltage that is in the off stage. This is not true in all multi-level converters, but it is definitely correct for many of them. So the lower switching losses stem from the fact that we have a situation in which the voltage on the device, here shown as an IGBT, is lower than the corresponding topology. We know that switching losses are mainly due to the overlap between the voltage and the current. This is the energy loss, and I'm showing here a turn-on situation. And also we have the output capacitor, which is dumped, or the energy is dumped into the device when it's turned on. All these are a function of the voltage. So if we operate the device with a lower voltage, the energy per switching instant will be lower, and of course the power, which is the energy times the frequency, will be lower. And then another issue is the lower conduction, which is primarily stemming from the fact that we are going to have a lower ripple current. And this is because the swing is lower than, say, in the buck converter, swing of the voltage here. And therefore the difference between this voltage and the output voltage is smaller, and therefore the delta IL is smaller, and the RMS seen by the capacitor and the ESR and the inductor, in fact, are smaller. Or we can, for the same ripple, we can choose a smaller inductor. So this is another benefit. And a third one is the fact that the voltage on the transistor with the off stage is lower. Again, this is not in all topologies. It is correct in topology we are going to discuss. And this is important also from the fact that in many devices, for example, a silicon MOSFET, RDS on is a function of the blocking voltage of the device. The higher the blocking voltage, the higher the RDS on, and in fact there is some breakpoint here for the case of silicon. And therefore you'd like to work at you like to use a device which has a lower blocking voltage, because the RDS on will be lower. So therefore this is another advantage, which is also lowering, of course, the losses due to the lower RDS on. Now, a key paper of the topology we're going to discuss is this paper here. It's a 1992 paper. It's a very nice paper. It's a fundamental paper, a pioneering paper, you might say. It discusses many multi-level topologies, and in particular it actually introduces the topology we are going to talk about, this flying capacitor buck 3-level converter. So they start off with this notion of using two transistors or two devices in series. So showing half a bridge. This could be a synchronous buck. And we see here that said this two transistors are conducting, and here we have the voltage on the two transistors. Obviously the voltage here is the maximum voltage, and if these devices are equal and the same, then the voltage will be split between these. Same thing here, of course. Here is 0, and here it's supposed to be split between the two devices. This is, however, not practical, because you never have two devices which are the same. Leakages are different, the temperature are different, so this is really a poor way to go, and very dangerous, in fact, because it could drift, and then one transistor will see all the voltage, and therefore this is not a way to go. So what they suggest is this flying, you might say here, a flying source, the voltage of which is half the voltage of the total voltage, half the input. And then we have 4 transistors which are synchronized. That is, when this is off, when this is on, this is off, and vice versa. And this is now representing the inductor. Now, in practice, we don't use a voltage source, we use a capacitor, which is sort of providing a constant voltage here. It should be large enough so the ripple will be small. And as we'll see, this capacitor is being charged and discharged such that in proper operation, especially if you have a control on that, the voltage will be kept constant, and it is supposed to be half the input voltage. Now this converter has two modes of operation depending on the duty cycle. For duty cycle smaller than 0.5 and larger than 0.5. So here is the case of duty cycle larger than 0.5, and I'll go quickly over the various configuration it'll take over one cycle. So when D1 is on, and again I'm labeling here D1, this is D1 not, so these are synchronized, and these two are synchronized. So then D1 is on, we see here the voltage, and D2 is not, then we see the voltage of the capacitor at the output. And then when both of them are not, we have a path here, so we see the input voltage here. And then when D2 is on, D2 is on, D1 is not, then we see here this path here, which is V in minus the capacitor voltage during this time. So all in all, we're going to see this type of a voltage at this midpoint. Okay, we see the input voltage, we see half the input voltage, input, half, etc. Obviously, we already see here that the swing is smaller. That is, the swing, the delta here is much smaller than the swing that you'll have when it is a regular buck converter. Now, what about the voltages on the devices? So let's go quickly over this. When D1 is on, we are in this situation, then D2 is not. We see a voltage here on D2, which is the capacitor voltage, and we see here voltage here, which is the difference between V in and the capacitor. So in both cases, we see that everything is okay. And same thing, of course, here. When these two are conducting, that is D1 and D2 are not, then we see here the input voltage, but at this point, the clamping point, we see the capacitor voltage. So the voltage here is V in minus the capacitor voltage, and we have a capacitor voltage on this device. So it fulfills the two objectives of lower swing and lower voltage on the devices. And the same thing goes in this situation. I'm not going to go over it. So what about now the situation that we have D smaller than 0.5? Well, in this case, it turns out that you need a modulation scheme which is a bit different. You see the difference here from here. So we have an overlapping here. And again, let me go over it very quickly. When D1 is on, we see the capacitor voltage. When D1 and D2 are on, we see 0 in this case. And then we see V in minus the capacitor voltage. And we end up with the situation that the voltage at the midpoint is now swinging between 0, but the maximum is half the capacitor, the capacitor voltage, or half the input voltage. So again, the swing is also very small, similar to what we had in the case of the duty cycle larger than 0.5. So we have here a 3-level converter. The 3 levels are the 0, V in over 2, and V in. These are 3 levels that we go through them, and this is the name comes from that. And now the question is, what is the relationship V out V in as a function of the duty cycle? Now there are many ways to do it. You can go dissecting all these waveforms and even writing differential equation. Let's do it in an intuitive way. And here is what I suggest. We start with the fact that P in is equal to P out. This is assuming, of course, an ideal system without losses. Now, what is output power? The average inductor current times the output voltage. what is the input power? It's the average input power, average, times V in. Now, if we define the duty cycle T on as this portion here, because this portion here is when D1 naught is on, okay? D1 naught is on. And this is the classical way of defining a duty cycle when you are connected to the input, when you're pumping in power. So this is T on, okay? So the average input current will obviously be the average inductor current times the duty, times this ratio here. And this brings this equation here. So that in terms of the relationship V out, V in, and duty cycle, it is the same like a regular buck converter, and you can show the same thing here, and the idea is of course exactly the same. If P in, P out, and then the time that the duty of this D1 naught times the inductor current is the average input current, and you come up with the same thing. So it's the same, exactly the same. So the benefits, therefore, are that we have a smaller swing at here, smaller swing on the inductor, and therefore we have a smaller delta in both cases, and therefore the ripple will be lower. A way to represent it is with this plot, which is a classical plot, and what we see here is the ripple, you might say, or the voltage difference on the inductor, which causes the ripple. And in the classical case, classical buck, you have a maximum at 0.5. This duty cycle 0.5 have a maximum, and this is the shape. Now, in the case of a 3-level, this is what we are getting. So not only that the value is lower, this is not to scale, of course, not only the value is lower, but we have a sort of a 0 point here, and the reason for the 0 point is that in the two cases, when the duty cycle is 0.5, you find at the midpoint V in over 2, which is the output voltage. So therefore, in this case, when the duty cycle is 0.5, there is practically no difference between the midpoint and the output, and therefore the delta is small, or theoretically going to 0, and this explains this 0 point here. So there is another issue which I already mentioned, and that is the stability of the capacitor voltage. There are actually two aspects to it. First of all, we would assume that if everything is equal, there will be an auto-equalization, but this will be only in an ideal system. So for that, you need a very precise PWM signal, which you cannot have, and also you need the same parameter for the transistors, the inductors, and the layout, which you can also never have. And also there is a startup problem. When you start up the system, the capacitor is discharged, you have to charge it to V in over 2. So there are many ways to do it, and I'm not going to discuss the startup. It's simple to do. Let's just talk about the dynamic stability. So how can we make sure that during operation the voltage on the capacitor will stay correct, that is V in over 2. Otherwise, not only that the operation will be incorrect and you have higher ripples, etc., but you may, of course, damage the transistors, because if you choose the transistors with a blocking voltage which is lower than V in, and if the capacitor is incorrect, has an incorrect voltage, then you may blow up one of the transistors. Now, as it turns out, you can do it by a closed loop, of course, with feedback, and the indicator is very simple, because we have seen that in each case we have an instant that we see at this point the capacitor voltage. Okay, for example, here when D1 is on, then we see here the capacitor voltage. So we can sample here. And when we sample here, then we can tell whether the capacitor voltage is correct or not. And if it is not, then we do have to adjust a little bit D1 and D2, or one of them, making one of them larger or smaller such that it will correct the capacitor, so it will charge a little bit rather than discharging it, and therefore it will correct the thing. So this is a way to go, and this is not too complex to build into the system. There are commercial units available for this type of topology, and I'm showing one of them. This is not an endorsement or recommendation, just an example. And this is the Texas Instrument unit, and this is actually for a charger. Now, they start with a higher voltage, and they charge a one battery, I guess, single cell. And since this topology has a high advantage in, of course, you get higher efficiencies here. So here's the unit they have, which is very nice because everything is within one unit. You have all these 4 transistors, all the drivers and control, of course, and obviously they have to, or they do take care of the capacitor, which is here. This is the flying capacitor. And in this case, it's a 20 microfarad capacitor. This is because the current is fairly high, it's a 6 amp. And then we have also a communication here outside, so that you can control the unit and adjust the current, etc. Now, you can expand this idea to higher level, that's more levels, and this will be done by, say, adding more transistor and more capacitors, flying capacitor as they are called. And this configuration is sometimes drawn this way. This is the same thing. If you look at here, the capacitor here, the switches, although this looks a little bit frightening, this is more user-friendly or engineer-friendly, but they are the same. So in some papers you'll see this construct. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting and perhaps it will be useful to you in the future. Thank you very much.